consent. Yes, very good. Grand. Cool. Well, it's lovely to see you all. Thanks for coming by. Monday morning. Some heavy R in first thing on a Monday morning is a lot to ask, but it's nice to see you all. So yeah, we'll continue our little adventure today. Today we can learn some new tools. It's just it's an introduction, really. If you haven't, or you've only dabbled in these things, to how to get the most out of our data and how to wrangle them and mash them using these tools that are part of this thing called the tidyverse, which we'll learn a bit more about today. So unit outline, learning outcomes for the day. We're going to, touch over some things we went over last week in terms of understanding what tidy data looks like, how to load it and save it. So getting stuff into R and getting it out, but that'll be pretty brief. And then the main one is learning this package, a little bit more about this package called DPlayer. And that's part of this tidyverse, and it helps us manipulate things in a way that's quite fluid and I think quite readable and quite shareable, and has some real benefits to it, especially for all the kind of common data bits of data manipulation that we do with scientific and ecological sort of data. And then, we'll learn if we haven't played with a pipe before, we'll learn how to weave these things into these elegant little statements that are nice and readable, and the computer is happy with them and human beings are happy with them, and to get our data to do exactly what we want, to do our bidding. In terms of our little pipeline, a little adventure that we're on, last week we did a bit on understanding what tidy data and tidy projects look like. So we sort of played around this end of the spectrum. And today we're wrangling things, manipulating our data into those forms most useful to us. And then next week, I love data visualization. That'll be a cool one. I wish I could run a course on that. It's such a cool subject. So we'll be doing a bit of that. And then getting into R Markdown at the end and how to weave these things into a little reproducible paper. But today, we're dealing with continuing our journey on our messy data. And that's the problem, is that they're often really just not in the structure and form that we want and that we need. We need to get our information out of there. How do we do so in keeping with our values of transparency and reproducibility, like we were chatting about last week? So we want to, anytime we manipulate our data, we kind of want to leave the raw stuff untouched, have this nice pipeline of nice reproducible pipeline of manipulation, so that we can see, well, okay, so here's how we got from here to here. I could do it again if I wanted to. I could share it with someone else and they could do the same thing. So it's really keeping with those principles of reproducibility and transparency. And now one such way to do it is by wrangling our data. And there's a new set of, it's not new actually, it's been around for a while, but there's these tools called the DPlayer and the tidyverse, and these are explicitly tools. They're almost a language within a language. I'll jump ahead one slide here. So the tidyverse is a set of R packages, and they're all related in some way. They deal with different parts of that little workflow that we were just talking about: importing data, wrangling data, visualizing it, modeling it, and statistically modeling it, weaving it into some sort of output. So they break it down into all sorts of different pieces, and there are a whole bunch of different packages that work together. It's kind of a language within a language, which kicks off lots of, when you get into the nitty gritty, there are debates as to how useful this kind of thing is. And it's are they sort of rewriting R from within? But we don't care about any of that. We can have some chats later if you want to, but basically that's all we need to know. It's a set of R packages that help us do things that we often want to do in R. There are lots of them. So in our little adventure, we'll be dealing with today DPlayer, which is one for manipulating our data. And next week, we'll be using ggplot2, which is for visualizing data. So we'll spend some time with these. There are a whole bunch of others. The main thing you need to know is you can actually install and load the whole thing by calling tidyverse here. So you can just install the tidyverse, which is a whole bunch of packages that work well together, and you can load it in the same way. So you just do library tidyverse, and that'll load up everything you need. So DPlayer and ggplot2 and all of these other things that at some point or another you may want to explore, or you may have no need for. And so we'll be calling on that a little bit today. So that's the tidyverse. And specifically what we'll be playing with today to help us wrangle our data is this package called DPlayer. And what it is again, a package that helps us change the form and shape of our data in flexible sort of ways and into the common forms that we might often use. Helps us extract information from our data in ways that we might also want to do regularly. And the way it basically functions, and we'll just do some examples after examples, and we'll mess around with some real data. It operates on the idea, part of what makes it readable and friendly, I would argue quite friendly for human beings to work with, is that it uses the concept of functions, which are verbs that do things to our data frames. So we have our data frame, and there are a whole bunch of functions in this package, and they are verbs, and they do particular operations on our data. They summarize our data. They let us select things. They let us filter our data, and we'll learn a handful of these verbs which help us do things. But that's part of what makes it a bit more human friendly than perhaps base solutions might be. In terms of what we actually do, as we'll see, what all of these functions and what the basic structure of our little workflow with DPlayer is. The first argument into our little sequences of manipulations, it's always a data frame. So we always start with our data. We have our data, then there are some verbs that we use, and they tell us what we want to do with that data, or we tell DPlayer what we want to happen to our data. So we've got our data, we've got some things that happen to that data, and then it spits out a data frame at the end. Data frame goes in, data frame comes out, and in between that sandwich are a bunch of verbs that help us manipulate that data in flexible and interesting ways. Technically, it's a data frame that comes out the other end. I've just flagged here. It's its own little thing called a tibble, but you don't need to worry about it. It's just a data frame, really, and it just operates slightly differently. And so here's a bit of a roadmap. And again, I'm moving pretty quick, but we'll slow down in a second, go through some examples. This is what we'll learn a bit about today. So in terms of reading data, we can use this function called Readcsv, which is slightly different to read.csv, which is the base R version of that. It operates exactly the same. It just basically has sensible defaults that we might like to use. And then these are the big ones. This is the meat in our sandwich that we'll be working with. We're learning a bit about pipes and what the heck a pipe is and how they work in R. And then here are some of these verbs that I'm talking about. So these are functions described as verbs, and they do things to our data set. So we feed in some data, and then we can select columns, or we can filter rows. We can mutate our data to create new information from existing information. We can count entries, we can arrange the results. And one that I use quite often is this: we can summarize our data in interesting ways. So you want the means and standard deviations of every sex by species. You can get multiple worksheets in Excel or whatever, or you can just have 2 little lines and it'll summarize everything by those combinations that we want to. And that's what we do with things like summarize and group by. So those are our magical verbs. And then once we're done, we can just shoot it out in a newly manipulated data set and save the results. So we won't spend heaps of time on those two. It's really these ones that are kind of the big new stuff. So I'll start at the start in terms of, so I'll work on, I've got one example that flows through here. I've given you this data set as well. So if you want to ever come back and reproduce what's in the slides, you can do that. You've got this in your little data sets folder. We've also got another data set, which is what the actual exercises correspond to, but you can follow along down the line if you want to. As I said, you can load up every package you need. So there are, with tidyverse, so tidyverse, that'll actually load a whole bunch of packages. For day-to-day sort of work, it's totally fine to do this. You just keep in mind that it is loading like a bunch of packages, I guess. And that can create a little bit of fragility, I suppose, because if you're loading 10 or 15 packages and you only need one, it's a bit wasteful, it's a bit unnecessary, but we're not going to go down that rabbit hole. So for now, I just suggest keep it simple. And whenever you need these things, just load up the whole thing and we'll worry about. We can chat about bloat and all that kind of stuff at another time and refining our workflows, but that's how you get everything we might need. Chuck the whole tidyverse in there. And to load data, we can just use this if it's a CSV file. So like we learned last week, it's a plain text file, so it's nice and simple. There's no fancy formatting or anything. You can just use this read.csv function. It differs slightly from the base version, from read.csv in a couple of ways. There are a couple of sensible defaults in there. Like it used to be different in that it didn't treat strings as these things called factors, although R doesn't do that anymore if you've got a new version. And it does a couple of other things that we don't need to worry about. But basically, it's another form of reading in our little plain text file. And when we do that, sort of read in our CSV file, and I've just said, here is my CSV file, read that in for me, please. I can show you this data set that I'm working with. So it's basically a data frame. It's actually, like I said, what's called a tibble. The main things are actually how it's just presented to you when you print things to the console like this. But we can, if we have a look at our data set here, we've got, I don't think I described it in the handout, but it looks like some kind of pretty standard ecological data set. We've got some unique record ID, month, day, year. There's some kind of plot. There's a species that was recorded in that plot. There's a sex of that species. And then it's the weights and hind feet lengths. I think these might be, I think I might have described it somewhere, but I can't remember, like rabbits or something. So we've got some hind feet lengths and weights of a bunch of different animals, genus, species, taxa, and the type of plot. So it's kind of a standard, I don't know, ecological data set. We've got replicates, different times of the year, different plots, and we've measured some things, specifically a couple of quantitative outcomes, the lengths and weights of these critters. There's a bunch of missing data and in places, as there always is. So that's our little data set that I'll be working with, and we'll be manipulating and wrangling and cleaning as we go through. But then one of the things that might be quite new to you if you haven't worked with this before is this thing called the pipe. It's quite cool, I think, and it's quite handy, but so we'll take a moment to, and it will form a key ingredient in the rest of our wrangling journey and our visualization stuff next week as well. So what a pipe does is it helps us express things, express chains and sequences of manipulations in a very human, readable, and friendly way, I think. So it's easiest if we just show you in a couple of different ways. So we can think about a set of actions that you might want to accomplish in your life. We want to find, and it's sequential, so you want to do these in order. We want to find our keys, you want to unlock our car, we want to start our car, we want to drive to uni, we want to park our car. There are 5 things we want to do. We need to do them in that particular order. If we were to make up some, pretend R code, what that might look like is something like this. If we wanted to do it all at once, just using base R, using raw R, in make-believe code, it might look something like this. So we always have to nest our functions and our statements. So here we start by finding our keys. We then unlock our car. We then start our car. We then drive our car to campus, say, and then we park our car. So there's our 5 steps, represented as 5 pretend functions. And in base R, you can kind of see once you want to start doing a bunch of stuff in order, which is something that we do all the time and very frequently want to do, can start to get a bit tough to track and read. And I actually think there might even be a parenthesis in the wrong spot there because that code doesn't run. So I just had to eyeball it. And you need to kind of count parentheses, and it's just easy to make mistakes, and it's not very friendly, and it kind of breaks one of our rules that we learned last week, which is things are run by machines, but code needs to be read by human beings. And this starts to pretty quickly get a bit unwieldy for us. But if we were to use our pipe, which is an operator in R, and you can kind of read it as being then, like a then statement. Do this thing, then do that thing, then do this thing. And just to show you what it means, if we do the exact, to rewrite that fake bit of code using pipes, what we could do is something like this. Find our keys, then unlock our car, then start our car, then drive me to campus, then park my car. So you've got those same four pretend functions, those 5 operations, all operating on your data. But by using pipes, we can express it in a way that is actually more akin to how humans think and speak and actually run operations in their real life. So what it's doing here is taking the results of one statement and piping it into the next, like a waterfall sort of flowing through these pipes. You take this, and then the results of this flow into this, which flows into this, which flows into this. And so you can do one thing after the other and build up increasingly complex and interesting and sets of manipulations, but it's nonetheless remains very readable. And you can trace it very easily. So if errors pop up in one little spot, or I don't need to worry about parentheses, because I can see it's just a list of stuff that I'm doing to a thing, right? You do this thing, then this thing, then this thing, then this thing, then this thing, and then it'll spit out some result. And so that's what pipes let us do. And I would argue and suggest that ultimately they create very readable code. So it tends to, everyone has their own preferences, so it's not universal, but it tends to create a more natural and sort of easy to read structure because it maps on a bit more closely to how we think. And getting people using code in the first place can be quite a strange thing, but if we just, and so this helps to essentially jot down a series of instructions, and one thing happens and then the next thing happens, and it can be quite a bit easier, make life a bit easier. A couple of other reasons is that now it's actually part of, so it's part of, they play very well, the whole tidyverse. So these things these tools that we're learning today are really built to play very, very well with pipes. So all of these fancy words and statements, and even next week when we're plotting and all that kind of stuff, they're all designed to work very well with pipes. So that keeps things nice and simple. And also the pipe is part of base R now. So it's just been recently integrated into R itself. It used to be a part of the tidyverse, but now it's actually a basic feature of R. So it exists. You'll come across it in the wild probably. So it's good, even if it doesn't really work for your style. It's good to know how it works because you'll be encountering it out there in the wild with other people's code. It looks slightly different in base R just to keep things, nice and keep us on our toes. This is what the pipe looks like. 2 percentage symbols and an arrow. We'll never type these out, so I'll show you there's keyboard shortcuts. You'll never manually type these things out. But that's what it looks like, the tidyverse version of the pipe, whereas the base version is this. It's the straight line thing and then a pointy arrow. So if you see either of those, that's what the pipe is. They operate very, very similarly, like almost identically, a couple of small differences with the base one, but nothing that will, I might briefly come across it, but basically they work the same way, start exactly the same sort of functionality and whatnot. So you can use either of those. If you use RStudio, you can tell it which one you want to use by default. But for this to work, you'll need a recent version of R, so beyond 4.1, I think. So if you're using an older version, this won't work, and it won't know what that is. So you might need to update to be able to have access to it. But yeah, either of those things, all of these examples, I think I've just kept it with this. I haven't updated it, so it'll look like that. So get some more real world hands-on examples here. Here's like again, essentially touching on just what we did before, but using it and showing you a few different ways of doing it. If we were to use base R to run, we've got 3 functions here, and we want to, operate them all on our data set. So here we've got my data right in the middle here, because that's how it always needs to be nested. I'm running this function called f. Don't know what it does. It doesn't matter. It's just pretend. So I've got my data. I'm running this f function, and I'm giving it an argument y equals 1, because it wants some argument. That's fine. I'm taking the results of that, and I'm feeding that into this other function called g. And g has this other argument called Z, doesn't really matter. Then I'm taking the results of that and feeding it into H, which is this last step. So I've run 3 functions on my data here. So I've got my data, I've done F, I've then done G to that, and then I've done H to that. So I'm doing 3 things, but again, these nesting is kind of building up. It's getting a bit complex to track what exactly is going on. So if I take that, re-express it in a pipe statement, it would look something like this. Touching back on I mentioned at the beginning, we always start with our data. So the very first step in any of these pipe statements that we use is always our data, because that's the most rudimentary thing. We need to manipulate objects. So here's my data, and then take my data. And what I want you to do is run F, this function F. I want to pipe my data into this function called F. Then I want you to take the results of that, pipe it into G, then take the results of that, pipe it into H. So again, I've just run those 3 functions again. My data goes through all 3 of them, but in a much more readable, traceable, modifiable way. I can add in steps here. I can remove steps if I decide I don't need them. Another thing, another intermediate sort of way that you might come across in the wild that you might have done yourself is that something like this, where you kind of save the intermediate steps of a process. So I take my data here and I run function F, and I save that to an object. And then I feed that object into this next function G, and I save the results of that. And then I feed that into the next function H, and I save the results of that. And that's ultimately what I'm interested in. So that's kind of a base intermediate version of these things. It's good. It's a little more explicit, so you can perhaps trace it. It's not so easy to get lost in all these nested brackets and things. But it's tricky because you end up with a bit of waste. You don't actually care about this. You don't actually care about this. A lot of copying and pasting going on. You really only want this, but you have to create these other messy objects to get there. It's still not always super explicit at a glance that these are all part of one operation, really, that you want to get done. Whereas here, that will only run by itself. So it's very clear that this one bit of data is feeding through all these. Whereas these I need to actually look at the fact that, okay, this goes here, gotcha, this goes here, to be sure that it's all part of one operation. So it's, you may come across that as well. But again, I think the piping ultimately has some benefits over both of these ways. And just a general thing to keep in mind, reiterating that so when you're creating a piped statement, you only need to specify the data once. So these things are all equivalent. And so it's always the first thing that we do is say, here's my data, and then here are all the things I want to do with it. You don't then need to keep saying, here's my data, do this thing on my data, do this thing on my data, do this thing on my data. The data is the very first up the top of your set of statements. So I'll show you what I mean exactly by that. And so you just don't need to, one common thing you'll trip up on if you're first using these is that you can just leave the data argument out of all those functions that you're actually using. So if we were to use a subset, which is just part of base I, if we were to subset our data, subset my data, and all I want is a data where the columns and rows where variable a is greater than 3. Cool. So that's not a piped statement or anything. That's just a standard thing that you might do. Here's the piped version of that. Take my data, feed that into subset. Take my data, then subset it based on the fact that variable a is greater than 3. But notice I've left off. So here, if you're just using the function by itself, you have to tell subset that this is my data. But because we do it as part of a pipe statement here, and the data is always the very first argument, I don't need to tell subset again what data I'm using here. So I can just leave that off completely. I can leave this data bit off completely. So here's my data, feed that into subset, give me the result when variable a is greater than 3. So I've just left off my data. Or it can be you may like to, if you're using this pipe, which we will be, you can actually use a little placeholder here as well. So the period mark here acts as a placeholder. So that's where my data argument would normally go. You can be explicit about it and put it in as a little dot. That is exactly the same as this. I would suggest just getting in the habit of thinking in this sort of way though, rather than using that. But these are ultimately equivalent. If you come across them in the wild, that's all that's happening there. I would say use this because this is one of those few cases where the native pipe, the one that's built into R, it doesn't actually work with this. So they decided not to include that. But it will work with this kind of a pipe. Yeah, so the main differences between these two here, as opposed to something like this, where I've said, take my data, feed it into this subset argument. Oh, you don't need to tell it data again, right? Because it's already part of my pipe. And the data is naturally flowing through those pipes into each function. So you don't need to tell it twice what data you're actually operating on. So this one in the middle here looks good, correct? This one, you've got that extra redundant bit because you're telling it twice what data set we're operating on. Whereas that's always perfectly explicit and clear because your data is always the first step in any of these pipe statements.
Tom, can I ask? Presumably it won't run if you try and put that in.
Yeah, exactly. It'll freak out and do something. We can try it. I can't exactly remember what it tells you, but yes, that won't run. But I'm not sure whether it's a terribly informative error or not. We'll have a look. That would, yeah, these will all be fine. But yes, no, it should stop. It'll break.
I have a quick question as well.
Yeah.
Will you be able to make an object with the pipe? So just name the subset whatever, or
Yep.
make the subset whatever. So just before the pipeline there.
Exactly. Yeah. So we'll do that. But absolutely. So you would just assign this as you would anything. Let me jump out very quickly. But all you do there is just assign it at the very beginning of a pipe statement. So let me just quickly data. Let's just reproduce this subset variable. Oops. A is greater than 3. So that's sort of what we're working with. And I'll pretend if we want to assign that to an object, there are a couple of ways you can do it, but I would suggest just doing it like you do in R already. So you just create an object. So new object, and you assign it to that. So you assign the results of this entire pipe to this new thing called, my new object, in the same way that you would normally in a non-pipe statement. So new object. So you could do it. Is that the data? Oops. Hold on. So those two things are doing the exact same thing, whoops, except they're spelled incorrectly, variable A. This is what you normally do every single day. Like up here, I've assigned this bit of data to here. Here I'm assigning this to here. With a pipe statement, it's the same. You just plonk that up above at the beginning of the pipe. You can do it like you don't see it often, and it's not a good idea because it's not very R-ish. You can do something like this, I'm pretty sure, where you can actually assign. You can do it like that instead. So you could stick it at the end of a pipe and say this into that, and then assign it to this thing. But it's not a very R way of doing it. And so you'll just confuse people, and you might even confuse yourself. But so I would suggest not doing it quite that way. So yeah, you absolutely can assign these things, and we will be. And you just do it the same. We just chuck a little assignment at the very top. Absolutely. Let me quit that because that keeps pinging. Yeah, great. So all right, so that's a bit of a pipe, and we'll get hands-on in a tick, but I'll introduce you to 2 new verbs first so that we've got something to pipe with. And then we can get into and just start messing with some data and figuring out how these things actually work. So I'll introduce you to your first 2 verbs, our tidyverse verbs. So these are functions which do things to our data, and they do things that there are actually a whole bunch of them. They put a cheat sheet in that little downloadable bit of, in that little package that I've sent to you. There's like a whole cheat sheet. There's a whole bunch of verbs. There are some, like all things, there are like 4 or 5 maybe that you'll just reach for in your day-to-day life, your day-to-day sciencing. And so we'll just tackle some of the more common ones that you might go for. So let's start with 2. We've got select and we've got filter, and these are just for chopping up our data. So our select is a function. This is our verb that lets us select variables in our data frame. And because our data are nice and tidy, our variables are always stored in columns. So if we want to select particular columns, we just reach for select. If you want to filter our data by particular rows, then that's what we reach for filter. So if you want, all rows where heights are greater than 10, then we're filtering. So we're subsetting our rows. So you want to grab particular columns, we select columns. If you want to filter rows, we filter rows. So it depends if you're subsetting by rows or subsetting by columns. And that's what these two things help us do. And we often do, there's often wasteful variables, pretend things, and we just need to chop it up and throw those out, or you only want the heights of the 10 tallest animals or whatever. So we can filter our data set by the values in particular columns there. Select and filter, columns and rows. I'll show you how they work. Select is for selecting columns. And to do that, all we need to do as part of our pipe statements is say, well, here's my data set. Again, it's always our data at the very top of our pipes, our little waterfalls. Here's my data. What I want you to do with that data is I want you to select these columns. And there are two columns in this data set called plot ID and species ID. All I want you to give me back is just those two columns. Select them, throw the rest out. I don't care what happens to it. And so if I run that little function, then it does. This is our ecological data set. There is a variable called plot ID and species ID. That's all I want to see, so just give them back to me. It's kind of like a simple kind of subset sort of statement, but it's just selecting those two columns and give them back to me. So if I want to keep columns, you just name them and you just list them like that. You could have a comma and then whatever columns you like. And that's how you select all the columns that you might want to keep. If instead you want to throw some columns out, so maybe you've got a big data set and you just actually want to drop a couple of them because it's like there's some notes column and you don't care about that, you can just put a little minus sign in front of them. So how this reads is take my data set here, then I want to select everything except these two columns. So I want you to throw out plot ID and species ID. And you can see here that these are all my column names, record, month, day, year, sex, hindfoot leg, plot type. There's nothing called plot ID. There's nothing called species ID because I've said, chuck them out. They're the only two I don't want to see. Give me everything else. So here I've selected just those two columns and it's given me just those two. Here I've thrown out those two columns and it's given me everything except those two. If we instead want to filter, so that's just that's about as the long and the short of selecting things. You name them, you either want to keep them or throw them away. So you either name things or just put a minus sign in front of them. Need to get a little bit more in depth with our filtering our data set by rows because we need to. These are all conditional statements, so we need to do a little Boolean refresher here, and we can get hands-on and do this in a sec. But basically, we use these things called relational expressions to filter our rows. So we've got in equal sign, we've got does not equal, we've got less than, we've got greater than, less than or equal to, greater than or equal to. These are probably the common ones that you'd use. Equals, does not equal, greater and less than. And you may just need to Google them the first handful of times. I Google all this stuff constantly, so that's perfectly fine if that's what we're doing. But I'll show you what I mean in terms of actually filtering these rows here. So what we do, how filter works is you say, here's my data. Now I want you to return me every row that meets this criteria that I've put in here. So give me every row where the variable year contains a value that is exactly equal to, because I've used equal to, and this means equal to. So give me every row in this data set where the value for year is equal to 1995. And if I execute that on my little ecological data set, I have a look, so it spit out all my variables because I said I want all my variables, I want the whole data set, but I only want the rows where year is equal to 1995. And if I have a look at my year variable, I'll see that it's 1995, which is exactly what I would expect, because that's what I've told it to do. Take my data set, my ecological data, filter out that data set by the variable year, and just give back to me those rows where year is equal to 1995. I could say where year is not equal to 1995, if I, for example, plonk that in instead. And that would give me everything, every row in that data set, except for those in which year equals 1995. What other examples have I got here? And you can tack on, and you can just plug a comma in there and add more and more criteria to get more and more complex sort of filters going on. So here I've said, we'll take my data set and filter it. All I want is the rows where the year is equal to 1995 and the month is equal to 12, or December, presumably. And again, if we have a look, I can see that in what it's spat out here is a data set with all my variables, because I said I want everything. But the year here is equal to 95. That's great. And the month is equal to 12, because that's exactly what I told it to do. I only want those rows where year is 95 and the month equals 12. And you can see I'll flip back between this one. That's just year equals 95, which you can see, but it's given me all the months. Now here, we've just got month equals 12 as well, because I said I want both of those things. Every year needs to be 1995, every month needs to be 12. And you can see how you can start to build these things up. You could perhaps add some slightly more complex filtering rules, or maybe you want year 1995 and every month except year 12, except month 12. And so these little relational statements might be a bit more complex. And some of our examples do get a bit trickier in that way. So you can chain these things together. And in speaking of chaining things together, so now this is the last thing before we'll actually get some hands-on and start to put this into practice a little bit. Where it starts to become more fluid and interesting and a bit more powerful is when we can start linking all these statements together to get some quite sophisticated manipulations of our data, but still in a fairly readable and fluid sort of way. So if I take my ecological data set, there's a few things that I might want to do as I'm just exploring, or I'm going to run some little analysis or something. I just want the IDs and the sex and the weight of all animals that weigh less than 5 grams. So if I was doing that in Excel, you know, you can think about how that might go. You'd have to sort things by weight and then lob through and then pick out all the unique examples of things. But if we wanted to do something like that, using just these tools that we've learned, it might look a little bit like this. So we could do something like, here's my data, ecological data. I want you to take that. And here I've said, so species, sex, and weight of animals less than 5 grams. So what you first might want to do is think about what you're actually asking it to do in terms of these verbs that we've just learned. So species ID, sex, and weight, those are variables. So I want 3 variables, which means I want to select those variables. But I want to filter my data set. So I only want those rows where their weights are less than a particular value. And so that would be a filter statement. So I want to select these things and I want to filter it by this. And so if we start to chain those together, it could look something like this. It can have, here's my data, take that data, and I just want you to give me those rows in which the weights are less than 5. And that will be all my animals less than 5 grams. But I don't just want that. I only really want 3 variables in the end. So from that, just give me those species, sex, and weights of all those animals that are less than 5 grams. And then from that kind of complex sort of goal there, statement, got this little bit of code, and that's exactly what it spits out. So here is every entry for an animal less than 5 grams, and it's just spat out those 3 columns, the species ID, the sex, and the weight of that animal. And so we've chained these, you know, relatively complex things together in one simple manipulation, haven't touched the data at all. The data, the raw data are totally fine. And it's completely transparent what we've done here. And once you get the hang of it, it's increasingly readable as well. So I've filtered out all those rows where weights are less than 5, and I've just selected 3 columns, species, sex, and weight. And I think we can, so there's a lot to take in there. We've just been doing some piping. We've learned a couple of verbs here, so select and filter. And I think I've got some exercises there if you want to hang out and grab a cup of tea. And let me just check our data set. Thanks, Julie. There's the data set link is just in there if you haven't got them. And so, yeah, look, maybe let's give it, 10 or whatever, have a bit of a read of and play with that data set, try and get the hang of. So the first couple of little exercises there, A, B, and C, that I've got in there, they don't actually use you don't need to load any data, they just use built-in data. And that's just helping us get familiar with rewriting things in terms of pipes. And then for D, E, and F, I've got a few questions there, like this, where we might want to use those two new verbs that we've just learned to actually do something to our data set there. So we can have a crack at those and converting thoughts into piped bits of code. And
Tom, there's a question in the chat.
cool. All right, let me have a look. Yes, or how does or work? Yeah, that's one of those. That's a good question. The question is, how does or work? Which is a good one, because that is one of those things that I mess up every single time. Yes, it does work similarly, I believe. So it's either or. I always forget which of those two it is. They work slightly differently, but in principle, yes, it should. So let's just try it. Oh, wait a sec. Sleep. Oh no, the pressure's on here. Feel free to read and whatnot in the background as I screw this up. So that's sleep. Let's have a look at no, wait, filter lifespan. Lifespan equals 38.6. 4 and lifespan equals 4.5. And something like that. Okay. Lifespan, no, so that didn't work. Hold on. Yes, there we go. So it does. You're exactly right. It does, and it's always the single. It's the single one. So the answer is yes. Or statements work just as they do in real life, but I always forget whether it's one or two because they work in different ways. But it's just the one. So this statement here, for example, that I just made up. So here's our little sleep data set, which I've given you and we'll play with. So this statement says, all right, I just want those rows in which lifespan is exactly equal to 38.6 or lifespan is equal to 4.5. And there's only 3 values there. Lifespan 38.6 or 4.5. So that's correct. So yeah, or works the same way.
Thanks.
No worries. I think I forgot to put that. I forgot to put that here. So I should. That's a good one. And let's get rid of that. Cool. All right. Yeah. So let's just chip away. Reconvene in 10, or if any questions crop up as you're going, please. And you've got some DPlayer. You shouldn't need a specific version of R. What can you tell me what warnings you're getting, just out of interest, Laura?
Yep. It says so when I say library tidyverse, it shows me all the packages that are working, but it says conflicts and the list is DPlayer. And then the warning message is saying like, oh, all of these were built in version 4.0.5.
Okay, what so no, I don't think none of that's urgent. I don't think. What do you know what version of R you are running, just out of interest? So you can type in version like that and it'll spit it out. It's not a big deal. Every now and then it's worth booting up your version of R if you're on an old one. So it's kind of painful, but if everyone, it's worth doing every now and then, especially if you're on something less than 4. I would definitely recommend it's worth jumping up. You can always see what version of R you're doing just by typing in version, VERSN.
I just completed a massive, great big upgrade of R, and then I went through a whole being on the network, so having restrictions on administrator privileges because you're in a network, and then I had to get administrator privileges, and then we did updates which took away the administrator privileges.
Okay.
Oh my God, it's taken weeks to get it functioning, but it is now all working. So I'm really sympathetic, or if you're having problems.
Oh, absolutely. No, I'm not. Yeah, you're exactly right. And I'm so I'm not trivializing it, especially if you're not on a personal computer, you're doing networks or you're on work computers and whatnot. It can be a complete nightmare. So a big jump every now and then is great. For example, now if you're on a version of R less than 4, it's probably worth trying to make the jump, but only if it's administratively humanly possible. And these should work irrespective. They're compatible to very old. They're friendly with very old versions. We can even have a look at what they should be compatible with while you're chipping away in the background there. Let's see. Its description, and it will tell you. So yeah, it should be totally fine on anything as long as you're above 3.4. It should roughly be fine. There can be some hidden issues, but so yeah, it should be good with old ones. And all those conflicts, it's just telling you that all the conflict is in R is that if you're loading up a package and it's got functions like things called select and filter and whatnot, if other packages that exist also have those functions, then those two things will conflict with each other. So if and because it uses some quite generic sort of verbs, you may hit cases where they do indeed. So one, there has to be some priority, and one will just override the other, because otherwise, if you've got a select function in multiple packages, R doesn't know which one you want. So that's all those conflicts are telling you, that you may have some other package loaded where there's also some functions called those things, but you don't need to worry about it generally. Oh, thanks, Aaron. Oh yeah, so you're right. Aaron mentions that even if DPlayer isn't necessarily, that works with like old versions of R, some of the more new ones do. So the tidyverse itself, yeah, you're right. It's probably 4.1 or something. Okay. Brilliant, some great help. Yeah, 3.6, that's fair enough. Oh yeah, the keyboard shortcut. Good question. So it depends if you're using RStudio or not. If you're using RStudio and you're using a Mac, for me, well, I'm using a Mac, but you can look in the help. So for me, it's Command-Shift-N, and that'll spit out your little pipe. I don't know what it is on Windows, so let's have a look at keyboard shortcuts help. So if you go to help, keyboard shortcuts help, it'll be in here. Don't know what it is for Windows. Where is the pipe? 1 second. Source editor. Insert pipe operator. This is what you're looking for. So for on a Mac, it's Command-Shift-M. Not sure what that'll do on Windows. So it'll be that. Source editor, insert pipe operator is the shortcut you're looking for. Control-Shift-M, thanks. And you can also, if you're on the, just as a digression, I think I found it the other day. So if you're on R 4.1, or so quite a new version of R, and you've got a fairly recent version of RStudio, you can tell RStudio which pipe you want to use now, because as I said, there's 2 of them now. There's that one that used to be part of the tidyverse. Now there's one in base R, and so by default you can say, hey RStudio, when I do my little shortcut, this is the pipe I actually want to use. And you can do that by going into RStudio, preferences, and it's in code, I believe. So here's a little box that says use native pipe operator. If I deselect that, and apply that, it'll show you what it does. It just uses the old one. So there's that other one. And it's also giving me an error here because it doesn't know what this means. But if I instead go preferences, code, use the native pipe, then when I do my little shortcuts, it'll be this pipe, the native pipe.
Do you find which one is more visually easier to read?
Um,
It doesn't matter.
Yeah, visually, that's probably a matter of taste. If you were to pick one and you've never used a pipe before, I'd probably say, I think I'd probably say go with the base one. So go with this one. If you've never used them, just because, you know, if we don't need to load a whole new package for this sort of thing, and eventually I think that'll be phased out anyway, this other one, because there is now a base, a native pipe. So if you're just new to pipes, first time you're kind of learning them, I would say go with the native one. So this little dash pointy thing. But I should say, sorry, that this won't, the pipe, it won't work at all. That native one won't work at all on older versions of R. So if you're on 3.6, that's not gonna work, sorry. So for your case, definitely use this one because the other one won't work. So there's another thing to think about. Sorry about that. So yeah, because they only introduced it in 4.1, I think it was. So if you're on an older one, only this one will work, because you need to load up the tidyverse to do it.
And I just noticed that in your note, there are, where you type the code, there's a space before the first letter you type.
Before there is where.
So you kind of, you can easy, when you have a hashtag, when you have a hash, like hash load data, and the lines after that, it always have a small space.
Oh yeah, okay. That's just
easy to read, but it's not on my laptop. I don't know.
I just do that. No, that's just a habit, and that's just me. And so, like mostly, a lot of people, I just do it because I find it easier to read. But that's purely a me thing.
I see. I thought it's like you have to set it so it can automatically start with this.
No, it doesn't. So I'm just hitting the tab key like every time I do something. So, you know, manipulate data, and then wait a sec. No, it does actually. It does start a new. Oh, what does it do that? It knows my style. I'd need to revisit why that's the case. But yeah, I just do that because it's readable. But you're right in that it automatically knows to indent my code slightly, which is nice. I think code indentation. Yeah, okay. That's probably an option in here somewhere. Yeah, I'd have to poke around. So I do it manually just out of habit, but you're right that it does actually automatically indent my code nicely as well. Like it does here. When we're chaining these things together, it'll naturally figure out what's part of a single chain or not, and it just helps with readability. But, yeah. And so this is how I loaded up. Oh, sorry, there's someone.
Which menu did you get your preferences from? Was it the
for like the pipe, I went into RStudio.
RStudio preferences. Okay.
Preferences, and then I was in code for the pipe one, and then it just here is use native operator. If you don't see that option though, it's either because it's probably because you're on an older version of RStudio. So you need to update R. R needs 4.1.
I'm not on a Mac. I think that's what it's. I
think it should be in that spot still. Yeah, I don't know.
I don't have an RStudio tab. So.
Oh, okay. It should be file. What's the equivalent? Sorry. There should be preferences though. Maybe it's in file preferences.
I'll find it. Yeah, and it's irrelevant. It's okay.
Silly Max. Tools options, says Aaron. Thanks. In tools options.
Tools options. Okay, thank you.
Yeah, sorry about that.
It's over the other side. Okay.
Let me pull up. So I'll just jot down the examples here we've got. Okay, so yeah, I'm throwing in a trick there as well. Okay. Oops, that's all right. We'll get to that. Should probably take that one out. Okay, so those are those ones. Yeah, so these first three just use built-in data. So no need to load anything for those. It's just kind of re-expressing things, and they should all run just fine. So yep. And that's a good way to test if your statements are working, because it should give you the same thing once you've converted those into pipes, which we can do. And I'll just flag that this third one's a little bit tricky because I threw in a curveball. So that one needs the use of that. That one needs you to use that placeholder, that little period mark. But that won't work with the base pipe because they made my life more difficult since I wrote these slides. So I'll probably remove that in the future. But if, just for this third one, just keep in mind that you'll need to use that little dot. The first two should be pretty.
I'm a bit behind here. Are we working through the exercises? The exercise.
Yeah, I think so. If that's that's pretty much. Chip away. If you hit a solution, feel free to jump in or throw it in the chat or anything. Otherwise, I'll give it another 5 minutes, and I'll work through those first three, and then the last three required loading up the mammal data and doing a slightly more complex operation. So I'll give you another few minutes for those two for sure. And as always, we may not get to go through every single one, but you're always welcome to just save it for next week or let me know or send through solutions as you like. But I think we're good for time. Stuck on C is yes, right. And you're right to be. So you need to make use of for C here, you need to make use of that little placeholder. That will be one trick, because these pipes assume that the data is the first argument given to each of the subsequent little functions. And if it isn't, we then need to use that placeholder. So this dot needs to go where your data would normally go. So that'll be one trick to getting that working. But then, sorry, just to make it painful, that's if you're using the native pipe, that's not going to work anyway. I'll show you in a tick. Ultimately, I'll just get rid of that example. But,
I have a question about the Readcsv with the dash.
yep.
So as long as I activate the tidyverse, like by doing library tidyverse, I should always use the underscore, or is it, or like would it change? Like, can I apply it to all the data that I use?
Yeah, that's a good question. No, so you definitely don't have to use it. If you're using the tidyverse, so one of the things it does is the tidyverse uses, instead of data frames, like I said, it uses these things called tibbles, which are data frames, but they're slightly different. So what read -CSV does is load up that data set as a tibble right off the bat. There won't be any hidden conversion of it to a tibble down the line. It also has a few other defaults that people find useful when it's like it gives you some more information, and when it prints things to the console, it does things in a slightly different way. It tries to be a bit more clever in guessing the kinds of data in there and whatnot. So it can be, if you're working within the tidyverse, it can just make sense to use this read-CSV because it's kind of designed as part of that workflow. But it doesn't matter, like ultimately, in most cases, it won't matter if you just use the base version, which is read.csv. I can do that right here. It still loads up my data. It might differ slightly in some of the guesses it's taken as to what is inside there. It'll print my data slightly differently. So you can see here, here's the tibble that it's printed. It always makes sure that just the correct amount of columns can fit on my screen. And it just tells me that there are more rows. You can see with the default data frame, it prints a lot more. And if there were more columns, it can run off the screen. And so the short answer is, functionally, it doesn't matter a lot. When you actually, I'd suggest if you're using the tidyverse, maybe just use all of their tools, because why not? But it's no big deal either way. It should work just fine, because once you start, if you feed a data frame into any of these functions that we've been working with, at some point along the line, it'll just get converted into a tibble quietly under the hood. So it'll end up that way anyway. But yeah, no big deal either way.
Thanks.
No worries. Good questions. What's a quick question in the chat? B and C, a subset and filter. Yeah, that's also just mostly a typo of my own. So yeah, you're right. Subset, and you could replace in B here, subset with filter. So that's kind of like an extra secret challenge that I accidentally put in there. But yes, you could use filter to do that exact thing that subset is doing. Subset is a base in base R, whereas filter is one of our magical verbs. Or maybe I did it intentionally. I can't remember. I wrote it a year ago. You could definitely replace that with filter. And if it wasn't clear as well, with the pipes and everything, it's not just tidyverse, like these magical verbs. You can use also all base functions and everything. All our stuff in principle works with pipes, so it doesn't just need to be things that are a part of this tidyverse. So as you'll see, so subset isn't, for example, dim, actually all of these. So these are all just base things that you might normally do. Look at a maximum value, grab the dimensions of a thing, subset a thing. But we can still weave those into pipe statements. So it's divorced from the tidyverse in that sense. No worries. All right, I might have a crack at this first one. Anyone repipe my, so str, what this is doing is asking, I just want the structure of this data set called MT cars. What does the piped version of that look like? It's all that data that comes first. And then there's the things that we want to do to that data. So that should probably do the same thing. So here's my, let me just double check. Yep, structure MT cars. Then if I run my piped version, we've got the same thing. It's a pretty simple case, so we wouldn't probably bother doing it that way, but it works nonetheless. I guess it's piping. It's not gonna work, is it? So in working out B, few things we could do. You've got to kind of unpack these things from the inside out because it's quite a complex nested little structure here. So first of all, where is my data? This is my data by the looks of it. It's this MT cars data set. So I'm going to pull that out. So that's my data set. And in our pipe statement, that always comes first because then I do things to that data. So now I need to figure out what's happening to these data and in what order they're happening as well, which may or may not be important, but nonetheless. So let's start unpacking. The first function I'm running on this is a subset, and it looks like I'm subsetting I'm pulling out all the rows where the value for sil equals 4. And in this data set, that's 4-cylinder cars. So let me just fully extract that, run it. Okay, sil equals 4. So that's what that's doing. But I need to chain it into my pipe statement. So I've already got my data there. I'm going to add my pipe. And then what I want you to do is subset that data, but only give me those 4-cylinder cars. And I just need to remember that I don't actually need to twice tell it that those are my data. So what happens if I do? It just gives you some uninformative error, which is not helpful. But there we go. So now I've got, here's my data, subset that. I'm getting the same result as if I did it manually the long way. So that's good news. Then what's happening to it? Dim. So I'm getting the dimensions of that resulting data set. There are no arguments being passed to that. So I should just be able to pluck that out and put it in the next in my chain. Dim. And what dim does, if you're ever unsure, you can always look up these functions, put a little question mark in front of them and type it in. And then that'll give me the help file. Dim just tells me the dimensions, how many rows, how many columns a thing have. Subset dim, and then if I run that, cool. All right, so there are my dimensions of empty cars, subset to only those 4-cylinder cars, got the dimensions, it's telling me there are 11 rows and 11 columns. That's great. And then the final thing I'm doing is getting the maximum of those two. So I want to know what's the biggest dimension. And it's going to be 11 because it's actually a square, which I could have thought that through a bit better. But the final operation, the final link in my chain will be this max. And if I hit that, the result I would expect is the number 11. And there's the number 11. So I know I've got there by unpacking that sort of one at a time. My cars, subset 4 cylinders. I want the dimensions of that, and I actually only want the largest dimension.
Tom, can you pop that in just pop the code in the chat?
Certainly can. The piped version of it?
Yeah.
Whoops, I just sent it to you, Aaron. Sorry, there you go.
Thanks.
No worries. And let me just see if I can replace subset with filter. Yes, I can. So yeah, I'll pop all my chat in the chat as I work through them. And this one, so they do escalate in difficulty. So don't worry as well too much if some of them get pretty hard, because the way I used to run these workshops the first time through is, we work through every second one or whatever, and there were some hard ones and we tackle them and come back and chat next week or whatever. So some of them do get pretty intentionally a bit tricky. So just don't worry. For the first time you've ever experienced a pipe or whatever, that you're not getting, exercise, the harder ones down the line, because it goes in the deep end. I would probably, so we can do this plotting one, but if it's stumping you, I'd just move on because that is a tricky one. And it's not, it's a tricky one. So I would jump into the ones with the real data. If you sort of got those two under your belt, maybe hop down into those ones that actually use our mammal sleep data. I'll show you what I mean with this pipe one now. We'll get this plot figured out. Yeah, so the trick here is that when we're using base plots, it requires our data, the data isn't the first argument here. So we need to actually use a little placeholder, but it's tricky because, yeah, it's my mistake and it's unnecessarily complex, but the native pipe doesn't have that placeholder. So this will only work if we're using this old one, or the previous one here, and I'll show you exactly what I mean. So where's the exercise? So gosh. So that's my data set, because that's it here. What I'm doing is I'm only plotting a filtered version of that data set. So I'm just plotting those rows in the data set where cylinders equal 4. So that'll have to be the first step in my chain. There's my data. I'm filtering that data, filter, such that I'm only getting those 4 cylinder cars. And that looks correct if I just have a look at it at that step. Cyl equals 4. That makes a lot of sense to me. I could even just run that little bit of code and see if it matches before. Yep, those look good. So I've got that bit right, and then I need to plot it. Whoops, I actually need to make it part of my chain. Plot. So we might try and do something like mpg as a function of disp and hope that works. But it won't, and it just gives you some ridiculous, complicated, some very unhelpful error message. The reason for that is because the way these pipes work, and another rule, which I probably should put in the slides, sorry, is that when we're piping one thing to the next, our data, these functions, so it all by default assume that our data is the first argument passed to these things. So it assumes that if we're not explicit about this, then filter is assuming that my data goes right there, that the first argument is always where my data is. And so here it's the same. So plot is assuming that the first argument here, these pipes are assuming that the first argument here is my data. But if the function isn't set up in that way, and we can actually have a look at plot, we're kind of getting into inside baseball here. So if you get a bit lost, that's okay. So the way plot works, it actually, the data set itself it isn't the first, it actually expects my X and Y variables first rather than the data set. So what I actually need to do is tell it to expect my data, but expect it back here where it would normally crop up. And there we're good at working. So the mistake there was just that it expected my data in that position 1, but that's not how plot works. This base version of plot works. So I need to use my little placeholder function here to explicitly tell it, no, my data goes there. That's my argument, which would be equivalent to that. That's a bit convoluted, and I'll probably just delete that in the future.
Could you pop that in the chat?
Really sorry, I'll get in the habit of doing.
That's right.
Actually, I won't work with it. You can get it to work with the native pipe, but it's convoluted and that's a whole rabbit hole. They just do things slightly differently. Unfortunately, this is the more convenient way to do it, I think, but won't work with native pipe. So let me just with my little solution. That's fine. You can also, yeah, you can also cheat. No, that's not cheating. I mean, if it works, it's not cheating. So you just won the game. That's all. Just to filtering out those rows that you only want. Yeah, which would work too.
But I have a question. For example, if I do that, you would be able to plot only those two variables. But sometimes I am interested in, for example, plotting one subset of points and then another. But I just wanted to ask if that would be more to take this object and use it for ggplot, or
sorry, ask me that again. Yeah, we could, we will and could use this. ggplot plays much better with pipes than base things do in general. So yeah, once we learn a bit of ggplot next week and we do these sorts of manipulations, yeah, you'll find that ggplot is kind of set up to work in these kind of piped workflows much better than base plots are in the first place. So in general, life should only get easier once we learn a bit of ggplot as well. Go away, Outlook.
Yeah, my question was that sometimes I would like to plot, like, for example, two subsets, one on top of each other.
Right. Yeah. Yeah, off the top of my head, we'd have to play with, I'd just have to see exactly the use case and whatnot, and figure out exactly what works for you. It's always also the case that pipes aren't always just the most convenient way to do it. So it might just be little inline subsets might be the best way to do it. I'd have to see what I know I've got the gist of what you mean, but I'd have to get a bit hands-on, sorry.
Yeah, makes sense. Thanks.
No, not at all. So that's ABC. For DEF, I'm going to start by loading up my data, and then I might have to begin to think about that. Yeah, so these are like word puzzles. So they're kind of, you've got to translate the question itself and our intent into individual bits of code, and then weave them together into a single chain. So it's, before we're used to thinking about this, before you start to internalize some of these things, it's a multi-step process. So it would be reading that question and just figuring out the steps that might need to be done, forgetting about chains and pipes and whatnot, finding the little function that does each single step of those things, and then starting to put them together into a list of ingredients that need to be done in a particular order. So that's how I've loaded my data. If you haven't, yours might be different here, but nonetheless, we can have a look at our sleep data. Yeah, there's all my rows and columns. Right. Slowly start to think my way through this first one. Using pipes, filter the data, include animals. So we want body weight less than or equal to 500 kilos. So if I'm just looking at my data as well here, body weight, I think I told us it's in kilos, isn't it? Yes, that's in kilos. All right. So the unit's already good. That's fine. So body weight, I'm just jotting notes to myself. So that would probably be one of them. I need body weights less than 500. And then I need to figure out how many records remain. So I need to find the size of the remaining, or the number of rows in the remaining data set. So there are two steps I can see there. I just want those animals with a body weight less than 500, and then I want the number of rows that are remaining, because that's what I mean by the number of records remain would be the number of observations, which would be the number of rows. And in R, you can actually just use n row. You can use this, or there are a few different ways to do it, and you may have come at it differently. You can also use something like dim, like dimensions that we did before. But those are my two steps. I think, translating that into there, except actually it's going to be a filter, isn't it? Oops. Body weight less than, which is what this is telling me. Not less than and equal to, just less than 500. Okay, so I'm starting to build it up a bit. The data I'm using is that sleep. And then if I start to chain these together, so take my sleep data, filter it, just to give me those body weights less than 500 kilos. And then tell me how many rows remain. So how many animals in my data set, or how many entries in my data set are animals with body weights less than 500. That looks-ish correct. Let me do that. And I get the end number 58, which seems sensible. Yeah. So there should only be a few animals, greater than 500 kilos. So that makes sense. And I will copy and paste this here to see if you all agree or if you got something similar. Also got 58. Lovely. A little typo in there. Okay, yeah, cool. Less than or equal to, sure, depends on your intent and how I've worded the question and whatnot, but it doesn't look like there were any animals that had exactly 500, so differences, hence no difference. But yeah, good point. No difference between that and that. Yeah, okay. Have you got anyone got just give me like the numerical, so number E asks how many variables are in the data set in the end. Without giving me your code, has anyone managed to get a number for that? So extend upon one, so what does it ask? Extend upon that. Also remove the gestation variable while keeping all the others. All right, so we just want to throw out one variable. 9, we're keeping all others. Well, we can have a look. So how many variables, if there are 11 variables in there, which is what this is telling, my sleep data set has 11, 1, 2, 3, 4, 11. If I'm just throwing one of them out, shouldn't it, or maybe I'm misunderstanding, it should just be 10, shouldn't it? Unless I've misunderstood. Let me have a look. No, cool. This is all just part of sanity checking and myself as well. So doing it manually and then actually doing it with code can be a good way of figuring out if you're on the right track. So all that's asking me is build upon that, but let's throw out this gestation variable. So selecting variables is one of our select statements. It's our little select verb. Select columns. And I'm throwing one out. So I could do it in two ways. I could give it the name of everything I want to keep, or I could just give it the name of the one thing I want to get rid of, which is probably the short way to do it. And I'm thinking gestation, is it? Gestation. So it would just be, so I've just added one extra step that I'm throwing out the gestation variable. Although it's also asking me how many variables remain. So I could also make a little tweak here. Our columns store our variables. So it's also just asking me how many columns are in the data set. So I could also tweak that last row there. And hopefully it gives me 10. So I've filtered my data. thrown out the unimportant one. I've got 10 variables left. Brilliant. Now what's the last one? As always, there are a few ways to do these things, and I've introduced a couple of tricky new concepts. So, if you start getting stuck at any of these points, that's totally fine. It may take a few cracks for sure. So here I'm looking for, well, it's always going to start with my data. So that's an easy win. Now I want brain weights. So here are my things are brain weights. That's the variable I'm interested in. I just want those animals whose brain weights are between 10 and 50 kilograms. So they're greater than 10 kilograms and less than 50 kilograms. So there are a couple of ways I could probably build that little statement. But even before that, it's a filter. So I'm filtering because I just want those rows which contain animals whose brain weight lands between these two values. So it's definitely going to be a filter. And I'm filtering their brain weights, filtering based on their brain weights. But how exactly am I doing that? So there are a couple of ways. Does anyone have like the filter statement that they'd like to share or that they've cracked? I've got two ways I know how to do it. Yep, nice one. That looks good to me. So there's a clever little this extra little function that I'd mentioned in the docs, but we didn't tackle explicitly, called between. And it does kind of what you expect it would do. We can read the help docs here, although my chat window is in the way. So we can specify if we can give it a whole bunch of numbers. So there's like a whole, 10, 5, 8, 7, 12, a whole vector full of numbers. And then we can just give it the two values, but we want to say, just give back to me those values that are between this and that. So between a small number and a big number. So it's a shortcut basically. So we can do it a long way and we can do it a short way, and we'll do it both ways just to show you exactly what I mean then. Let's do it the long way first. Do you know what anyone get the long equivalent of this? So what do I want? Between 10. So brain weights. Oops, sorry. They need to be, if it's between 10 and 50, they need to be above or equal to 10. Or yeah, that looks good as well. Excellent work. I don't know if I said equal to, did I? Between, so no. Okay, so let's say I need those animals whose brain weights are greater than 10. And so we're actually using some of our relational expressions in here, because they need to be both above 10 and below 50. So brain weight below 50. So that should give me all those rows in which brain weights are both simultaneously above 10 and below 50. Or the exact same way we could write that with this fancy version. I'll make version 2 down here. We could use a between statement, which is between. So here are a bunch of brain weights. Missing a column. And the way this between function, if you can bother using it, is it wants a whole bunch of values, and then it wants the small one and the big one that want to set the bounds to what you're getting back. So these two things should be the same. Here's my data set. Filter those brain weights that are simultaneously above 10 and below 50, or doing it in the exact same way. Give me those brain weights that are between 10 and 50. Let me see if that works. And just by eyeball, those look about the same dimensions, same values, just eyeballing it. Cool, so I think we've done that, and looking if they look sane. And yes, is the short answer, absolutely. Earlier, the chat, you could do those filter statements. Actually, so there's a third way we could do it. Yeah, for sure. Yeah, absolutely. If you wanted to, we could do that. So filter those that are above, and then filter those that are below. It's just a slightly longer way of doing it, but you know, whatever works. And maybe it's easier to think about that in the first way. So as multiple steps, and then you'll have a look at that and go, oh, actually, I can combine all those. Yeah, that should also give you the same thing. And it does. Yeah, 14 by 11. Yeah. It's just whenever you see yourself duplicating statements like that, typically they can be combined. So unless there's some radical change, because we can get quite complex and like do some other things to the data set or like create new variables or whatever. But typically if you see multiple of the same function in between, they can often be combined. But yeah, that's actually a third way we could do it for sure. So those are all doing the same thing. And what else was the last thing I wanted us to do with that? Oh, and throw out any rows in which there are NAs in the lifespan. A bunch of ways to do that, but yeah, I think I've mentioned there's this drop NA. Oops. Lifespan. So drop NA again, if I'm not sure what that is, I'll just look at the help file, drop NA. And what does this do? Drops rows containing missing values. Okay. So I give it, if you, so you can feed it a particular variable, and so what this is doing here is saying, look, if there's any NA whatsoever in lifespan, I just want you to chuck out that whole row to get it. I'm not interested in that whole data. And so that's all this little extra little bit here is doing. And if I tack it on there, I could tack it on there, and they should all be exactly the same now. So I've got my sleep data, just getting those brain weights between those two values, and throwing out all those cases in which lifespan contains a blank value. So that should be the same, that should be the same, that should be the same, and they look good. And I'll paste them all in the chat. Those are my little solutions. Good, great work. Cool. So I know that's like a lot to take in, and we all may be at different spots and stages. If there's anything else, if there's anything, just ask if anything at all crops up. If you kind of got the gist of the, the first one or the first couple of those, and they're starting to make some sense, even just reshaping these things up here, then that's great. You're doing well, because the first time you've maybe perhaps have met pipes as well as all of these new verbs and ways of thinking about things. But if you can at least start to just slowly follow the logic behind these things anyway, that's great. And just getting into the flow of it and going over it a few different times. As I said, this last one, they get pretty complex. They ramp pretty quickly, and I did that intentionally. But that's a cracking. We might crack on then and learn some new words, some further words. Let's see what's next. There was a lot there. So you're doing extremely well. To get piping, to get filtering, to get subsetting, to get chaining things together. It's kind of a whole new, it's a language within a language, as I said. So now we'll just build on those foundations, but that's arguably the biggest leap is now behind us in terms of even thinking in terms of pipes and all these sorts of things. And I'm constantly Googling functions and whatnot. So Google is your best friend. when it comes to these things. Or you've got your cheat sheets as well. This is kind of a cool one. So this is a new word, another, we'll tack it onto our vocabulary. This helps us create new columns and create new information, which is something that we might often like to do in our data sets. Whereas in Excel, you punch in formulas, standard deviation equals that, divide, or the mean equals the mean of all these rows or whatever. We create new columns all the time. And if we want to do that and build out our data set and derive things from existing data, then mutate is what gets us there within this tidyverse framework. So what mutate allows us to do is add new variables whilst leaving everything in place by default. We can actually overwrite things in the data set, but typically you often don't need to or don't want to. So by default, it leaves everything untouched and just tacks on new information based on the instructions that we give it. Mutate. So let's crack on and do some examples. Sticking with that same data set. So we've got our weights here in our original data set, and they were, as I jotted down in the initial description of the data, they're in kilos. Yes, body weight, total body weight of the mammal in kilos. So if we're, say, interested in weights except in, no, sorry, I take all of it, or my slide's incorrect. I might have total body weight of the mammal in kilos. They're in kilos in the data set. So I think I've got that, perhaps the other way around in the slides, which I will fix up. But if you wanted to convert them, for example, and convert weights kilograms to grams, they're already in kilograms. Slight detour there, sorry. Nonetheless, if we're doing this, we can create a whole brand new variable based on information that's already in our data set. And we just do it by calling this mutate variable here. So if I take our weights, I divide them by 1,000. So we've got here's my data, again, at the beginning of our pipe statement, always just the data. That's a win. Take my data, then I want you to mutate that data set. And what this is doing here is saying, I want you to give me a brand new variable called weight kg. And I want you to build that from existing information in my data set. And every value in weight kg, that should be equal to weight, which is already a variable in my data set, divided by 1,000. So take everything in my weight variable, divide it by 1,000, and save the results in this brand new variable that you're making for me called weight kg. I'll say that again because there's a few things going on in here. Take my data, mutate it, and I want you to create me a brand new variable here called weight kg. And how I want you to build that is by taking weight, which is already in my data set, just dividing that by 1,000. And then to show you the result here, I've also added this little statement head, which just gives you the top 10 rows of our little data set. And that's what we've got. And you can see that now tacked on the very end of our data set, there's this brand new variable that's not currently in my data set or in yours called weight kg. And we'll shoot in there and we can inspect it. And in that, I would expect that to be exactly equal to weight divided by 1,000. And if it's NA, it'll just be a bunch of NAs. So that's a bit of an annoying example there. But that's all it is, and that's how it works. So here's my, save the result here. Here's my new variable that I want you to create for me. And here's how I want you to create it from information that's already existing in my data set. So that would be like a simple conversion, for example. You can imagine all sorts of things we might like to do. And then we can get a bit more complex. So building up into our chains here. Let's have a think of what this one's doing. So here's taking my data. Select means I just want those variables, genus, species, and weight. So just give me those three. Don't care about all the other 7 or 8. Actually, I only want you to do this for those data in which there is a value for weight. So that's what this is. Or we could have used that one we just learned, drop NA. So we could basically throw away anything that is a non-existent value. That's what this looks like it's doing to me. So I only want you to run this operation if they actually have weights. Good stuff. Then create this new variable for me. I want you to save it and call it weight kg and tack it on the end of my data frame. And how I want you to create that is by dividing the weights that you've already got by 1,000. And now we can actually have a look at what's going on here. So you select genus, species, weight, genus, species, weight. So I would expect to see those. That's great. I wouldn't want to see any NAs. Good. And I want here in my mutate statement, I'm creating a brand new variable called weight kg, and I'm tacking it on the end. So that's what this is. And the values of that should be equal to weight divided by 1,000, which is exactly what it looks like we've got here. 218, 0.218. So these are that divided by 1,000. So you can see exactly what's going on there and what it's done to achieve the creation of our new little variable here. And in doing so, we haven't had to click around or copy and paste data or do anything like that. We've got our raw data that we've never touched. We've got a nice tidy data set at the end of it. And we've got an explicit set of instructions that told us how to get from A to B and create these new derived data. There's absolutely no mystery whatsoever as to where these values come from, because it's beautifully well documented and preserved right here. It's dead straightforward as to how we got there to there. And we could do it again 1,000 times if we needed to. Again, just to, to keep on our adventure and building on the complexity here, just as we can have like multiple filter statements or multiple select statements, you can have multiple mutate statements, and you can actually build upon things that you already create within your mutate statement there. So if you create a brand new variable in mutate, you can then in the next row or in the next call to mutate, build upon that variable which you just created, as long as it exists and you're doing it in that order. And so I'll show you what I mean. If we jump between these two, the only difference here is that I've added an additional line in mutate. So not only am I creating a brand new variable called weight in kilograms, which is the result of dividing my weight column by 1,000, weight kilograms, yeah, weight divided by 1,000, that looks right. I'm going to use that brand new variable called weight kilograms, and I'm going to create another column called weight in pounds. And so here I'm just saying, use what you've got, tack on this weight underscore pounds column, or variable rather. And what I want you to do is to derive that, I want you to take this brand new thing called weight kg, which I just created right here, but that's fine because R runs things line by line. So it goes this line, then this line, then this line, then this line. So by this point, weight kg exists. So take that, times it by 2.2 and save the result in this new variable called weight pounds. And if I have a look, and I see, okay, so weight pounds should be this value times 2.2. I could do that manually, but you can see that it is indeed exactly what we would expect it to be. 0.2 times 2.2 is 0.44. Great. So I can see what it's done here again, can trace it all the way through. And we just got a little bit clever. So we created a thing, then built a thing on top of that thing, which you might actually want to do sometimes as well. And that's how we add new information in a transparent, reproducible way to our lovely data sets. And then it'll just give you the top. And that's just getting more and more. Yet another example. So it's just, this can go on endlessly, of course. So we can build on things and have quite long mutate statements. If you're building new rows based on data that came before it, that's just another one. So there's one in tons as well. Although I think I've done that wrong anyway. Done this one wrong. But nonetheless, the point stands. So just separate it by a comma in the same way that we would with our filter statements, with our select statements. This is selecting on all these things. This is mutating all these things, just separated by our little comma here, our little statements. And as long as the one that comes after is based on information created in a step before, you're fine. So if I tried to, if these two were swapped around, weight kg wouldn't exist at that point, so it would just fail. It would tell you something like, there is nothing called weight kg because we haven't created it yet. So I think we just dedicated mutate to itself. I'll leave that one there, and we've got, it's I think sort of one exercise we've got, but it's kind of a long one and it combines a few of our powers that we've learned so far. And so it really takes a little bit of building up, but it draws on mutate here to get to our answer. And I'll leave that on the screen there to get a sense of how that goes. Oops, sorry, I moved that. So that's our mutate. Leave that to one side, whilst I also, oops, continue to think out loud here. I'm still using manual. Okay.
Sorry, Tom, are you doing a particular exercise?
Oh, sorry. Whoops. It's the next one. Just in there. It's sorry about that. In a single statement, create a new data frame. So there's like 4 steps to it, but it's all, we're trying to weave it all into one statement. So it's the next one, W1A-2.
Oh, got it. Okay.
Sorry about that. Yeah. W1A-2. Give us all a minute or a few. So this really takes some breaking down, this one. It's not a dead straightforward. There are 4 steps. They need to be done in some order. They're slightly different. They draw on all 3 of our skills so far. So our selecting, our mutating, and our filtering. And we need to save the result as well. There's quite a bit going on. I'll just start thinking it through a little bit. Right. So we need a new data for there's 4 things or 5 things, I guess we need to do ultimately, because we need to assign it. So we need a new data set called mammal subset. I'm going to assign it to something called mammal subset. So I can tick that off. And my data, I'm using the mammal sleep data that I've already been using. So that's great. That's always my first step in my nice chain. So I can tick that off as well. That's an easy win. So there are 4 things: only contain complete cases, excludes a bunch of things, excludes a bunch of rows, and it needs some new data in there. Yeah. Okay. So I could go through and maybe assign each of those to we've got a few steps in there, but those are our magical verbs that we've just learned. Except for the only complete cases one. So for that, I can call on this, which is what we learned as part of the kind of off to the side as part of our previous exercises. So this drop NA function, which here's my little help file here, which I can always have a look at. Let me pull this up wider. If you don't feed it any further information, it actually just throws out every single row that contains an NA anywhere. So you could use that if you only want fully complete records. You just hit it with drop NA, and it'll throw out every row in which there is an NA at all in there. So it'll be throwing out Arctic fox, it'll throw out Genet, it'll throw out the raccoon, it'll throw out all of these, because these all have NAs in there, so I'd expect them all to be completely tussed. I can actually just run that little bit and see if that is indeed the case. What have I done? Oh, dat sleep, that's because I called it the wrong thing. Dat sleep. There we go. Now there's no more NAs in my data set because it's thrown out every row that contains one. Whether or not you want to do something that extreme is up to you, but that achieves our little goal here. So that's kind of step 1 ticked off, really. So the data only contain complete cases. I've thrown out all those NAs. Next step. Excludes some variables. So if we're dealing with grabbing variables, that'll be a select. And because there are a whole bunch and I'm just excluding a few, it's probably just to explicitly throw out those ones that I don't want. And I do that with my little minus sign. Predation, exposure, danger. Oops. And building it up, I'm just going to run that by itself and just to see, it should look exactly like this, but it'll throw those last 3 columns. So I would expect just to see this little chunk here. And if I run my code, checking my insanity, cool, that looks correct. Thrown out those 3 things. Okay, so that's step 2. That's making some sense to me. Okay, only includes records with gestation durations greater than 12.5 weeks. So there are a couple of things going on here. So then if I look at the next one as well, and if I think about my data set, so gestation, these are currently in days. So if I want to only include records with gestation durations greater than 12.5 weeks, I'm either going to need to be a bit clever about how I specify which rows to keep, because these are in days. So I need to do a little bit of filtering on the fly. So I need to convert those into weeks or figure out, how many days, half a week is. Or I could start with part D there as well and just reverse the order of those two, because I need to create records. I need to add body weight in grams, and I need to add gestation in weeks. So I need to do some unit conversions there as well. So I could do that first and then just filter based on my new information. Or you could filter, do a bit of conversion on the fly, and then add the new things. So we can do it both ways, but I might keep it simple for myself. So I'll start by creating that new information. So I'm going to start with D. Now it is a mutate statement. What do I want? So I want body weight in grams. So I'm going to create a whole new variable called body weight. I'm going to call body weight G, body weight grams.
Sorry, Tom, could you just put the last one in the chat? Because I've got an error message. I can't work out what I've done wrong.
Which last one, sorry?
Just the first part of that, thank you. Yep.
That little part.
Yep.
Yep. I'll give you that part instead of assigning it.
Thank you.
What's it grumpy about? Feel free to.
It just says error in drop NA, could not find function drop NA.
Oh, that's part of tidyverse. Is that so? If you run, so you've installed the tidyverse, it should load tidyverse as well. But if you run, can you run? Do you have tidyverse loaded up? All right, or maybe it's you run that a little bit. What does it say?
Yeah, if I paste your code in, I'm getting the same error. But don't let me hold you up. You can.
No, I'm just. So my guess is maybe just forget about that for now, because it's probably, if I had to guess, what are you on Are you on like the newest version of R or?
Yeah.
Okay. Something wrong with the tidyverse package. Then it's either not loading or it's not installed correctly for some reason, because it's part of that. But okay. So if you just throw that out, it actually shouldn't. You can still run the other stuff.
Yep.
No, but that's cool. So I'm going to create. What am I going to do? I'm going to create a couple of new variables: body weight in grams. And so it's currently in kilograms. I was mixed up in the slides, but that's fine. So I'm going to do body weight divided by 1,000, because that's how we get from kilos to grams. So that will create this new body weight G from body weight divided by 1,000. I can just, again, doing one thing at a time, I'll build that up. Body weight, that should be this divided by 1,000. Yep. Doing a bit of a sanity check as we go. That looks sensible. And the other thing I wanted to do was gestation in weeks. I'm going to create a new variable again. Gestation, call it gestation W or whatever you like, WKS. Yes, you're exactly right. So yeah, thank you very much. We'll just ignore that. You're exactly right. Going from kilos to grams is multiplying, not dividing. Thank you very much. I need to go through and figure out what units I've actually done throughout, but yep, you're exactly right. So that should indeed be multiplying from kilos to grams. Gestation in weeks. So where am I going? So these were, what is it? It's currently in days. So we can just divide by 7 and that'll give us gestation in weeks. Is that correct? It's definitely in days, isn't it? Yep. In which case equals. So gestation is currently, oops, divided by 7. So here I'm saying create this brand new variable called gestation in weeks. And all I want you to do to get that, populate it with gestation divided by 7. So that's, and gestation is in days. So let me again, on that little chunk, 6. And if I have a look at gestation here, 42, 6, that looks right. 624 days is about 89 weeks. Yep, so this looks sensible to me. So I've got now gestation in weeks as well. And so for my final step, where it was asking what I wanted to do was only include records with gestation and durations greater than 12.5 weeks, I can just filter on that new variable there. So I could just say something like filter based on that gestation in weeks greater than, what did I say, 12.5. So that should do exactly that. So throw out all those cases that are less than 12.5. If I do that, fantastic, there's nothing 12.5, that looks right. And to actually assign it to something, that's all this is doing up here. So I've assigned this entire statement. So that's quite a long, I'll pop this in the chat here, sorry, one sec. You can see that was quite a long and multi-step process where we wanted to do some quite complex things that would normally take a very long time. And again, until it takes time to begin to internalize these things, but you can see how we sort of, or how I would anyway, begin to break down a problem like this. We start with words, like a verbal description of what we want to do. We break that into individual little pieces. And we try and sort of map those on to our knowledge of these little functions that do particular things, like select particular rows or throw out particular variables or create new information. And again, we're just building it up piece by piece. As I was going, I was testing individual lines. I didn't try and write the whole thing at once because I just never get it right the first time. And so we built it up, checked it against our own understanding as we went. And then in the end, we've got this quite tidy little statement here that does some fairly complex operations on our data and saves the result for us, but in a nice, clean and sort of reproducible way there. Thrown out lots of info, saved a few variables. But it took time and brain power to get us there. And so it's not by any means an intuitive thing right off the bat, but in time, I would suggest that it's worthwhile. And get us a very long way. So that was mutating, was, is, and will continue to build. I think we've got one more big one. One more big one and a few kind of smaller ones. But this is quite a cool one. And this is one I use very often, these new words that we're going to learn now, summarizing and grouping our data. So this is a really cool way of pulling out information, summarizing information in quite large and complex data sets, which is often what we want to do. What's the average and the standard deviation for each of these sexes, or for every combination of sex and species? What's the sample size, for example? Those are all the kinds of common little bits of information that we often want to pull out. And that's what our summarize and our group allow us to do. So here's our verbs. And there's a few on the go at once here. So these are little kind of incidental ones at the end, but really the big ones that we want to focus on are summarize. So what summarize does is create a whole new data set, a whole new object, which contains summary data. And it summarizes in the form that we'll tell it to. And there are lots of different things we could do, but we'll go through a few. And group is a helper function. So you always use this. In summarize, you can just use by itself, but almost always you'll see these two things playing well together, because you may just want to summarize an entire data set, for example, like just what's the average of this, or what's the standard deviation of this. But there'll often be some grouping structure in your data set as well, plots or sites or replicates or species or whatever. And so you want to get summary information, but by groups. So each sex in our data set, or each combination of sex and species, or replicate or day of the week, whatever. So whenever there's some grouping structure and we want to get some summary information out, these things go together hand in hand. And then these are just a couple of extra little helpers that we can make with. We can arrange the output if we want to sort them, or we can count, and for things like sample sizes or number of unique entries. But these ones are the big ones: summarize and group by, which we just spend a little time on. And so the logic by which they work is a thing, and you may come across it out there in the world, or it's kind of in a bit of programming jargon, and it's called a split, apply, combine strategy. So what this is doing under the hood, and we're offloading, and it's doing by itself to save us the effort of doing it, it splits up the data into groups. It applies some function or some analysis to each of those groups, and then it mashes the results back together. So if we wanted to calculate the mean for every species and we were doing it manually in Excel, we would have to split up the data into our sexes, apply the function mean to each of them, combine them back into one holistic result. What's this? And this is just doing it exactly, that's called the split, apply, combine strategy. It's just doing it under the hood for us. So that's basically what's going on. It makes it much easier because we can do much more complex and interesting things, but without all the fuss of manually clicking around. So here's an example. If we've got our ecological data set, what I'm telling it here by using this summarize function is I want you to create me a whole new data set, because summarize always creates a brand new data set, because it's a very different structure to what we're putting in. So take my ecological data here, and I want you to summarize those data. And for the output, what I want is a variable, a brand new variable called mean weight. And to get that, I want you to, so the contents of mean weight, I want you to take the mean of this variable called weight. I also want another variable. So here's my comma, because I can chain together some statements here. And I want this brand new variable called SD weight. And the contents of that, what I want you to get for me is the standard deviation of all our weights in our data set. And this is in here as well, just because I want you to, it can freak out. It doesn't like NA values. So I've just said, in all those cases, just get rid of NAs, ignore them. Okay, so forget about those. So by feeding this in, what I would be expecting is I want you to take my entire data set. I want you to look in the weight column, and I want you to calculate the mean and the standard deviation and save them in their own little variables here. And so what it spits out is a whole new data set. There's only 2 values in there because it was summarizing the entire data set. There's no grouping structure whatsoever. And it's given me mean weight, SD weight, because I told it to. I want these 2 new variables. And the values, what I want you to fill those with is the mean of all weights and the standard deviation of all weights in my data set. And that's what it's done. And that's the output right there. So it's a brand new data structure, brand new data set. We can't tack it onto our original one because it's a completely different shape and size. So it's a whole new summary data set that's just summarized some fairly simple little bits of information that we might want from it. If we wanted to step up our game a little bit, as I said, and there's often grouping structure within our data, then we can use this group by function. And so you'll see that my summarize is exactly the same, nothing different there. I want 2 new variables, one that contains the mean, one that contains the standard deviation. But here, by including this group by variable, group by function, and grouping by this other variable in my data set called sex, what I'm saying is I want these, but I want them for every unique combination of sex in my original data set. So I want the mean weight, I want the standard deviation weight, but I don't want it for the whole data set at once. I want you to group it by this thing called this other variable that I've called sex. And there are actually 3 values of sex in that data set. There's F, there's M, and then there's NA. So there's like empty data. So we've got, again, a brand new data set here, but instead of just having 1 value for mean weights and standard deviation weights, we've got 1 value for each of my grouping variables, each level of my grouping variables, M, F, and NA as well. So you can see how these 2 things are kind of playing together, summarizing my data by this. And if there are multiple combinations, which I think is what this next one does, so just like we can separate multiple arguments by commas for our filter or our all our select statements. If there are multiple groups, multiple combinations of groups that I want to actually summarize my data by, you can just tack them on. So here, the way to read this is saying, again, summarize my data. I just want the means and standard deviation weights, but I want it for every unique combination of sex and species in my data set. So not just crunching the whole thing, and it's not just by sex, but every unique combination of sex and species ID, I want you to give me a mean and a standard deviation weight. And then you can see the beginnings of the output here is actually longer than this because there are quite a lot. But you've got female of this species, female of that species, female of that. And if we went right down, you get male of each of those species, male of that, male of that. So for every pairwise combination of these groups, I want that summary information. You can see that's the kind of thing we would often want to do in our data sets. That's a very common sort of thing by getting quite complex summary data, and it's not just means and standard deviations and it's errors and it's all sorts of things, but in relatively few statements here, we can go a long way and get some quite complex summary information just from from these larger data sets. And just to tack on a couple of extra useful little verbs to expand our vocabulary. It can, if like you're eyeballing things or you just want to arrange them a bit, it can be useful to, I guess, rearrange the results of our little queries there. So for example, you could sort your data if you wanted to by weights. And that's what we can use this arrange verb for. Here you can see by weight, so it's from low to high by default. We've just take my data set and arrange it according to the values that are contained within weight. And it's done that. And so those go from low to high, just the same as sorting in Excel, basically. Or you can, it can be useful when you're interactively, messing around with your data and poking around at these things too. We can, of course, include these in our chains. So here, for example, I've got take my data. For every unique genus in my data, I want you to just give me the average weight. But before you output those, I want you to arrange it according to the ascending weights here. And then just show me the results here. So you've got the lowest weight little genus here is Perignathus, increasing up to, not going to try and guess how to pronounce these. Then it goes on and on. So you can, it's just if you're interactive and inspecting things, it can just be a useful tool in your little kit to arrange the output according to some variable. It's also common, as I said, sample sizes are a thing. And so we may often want to just count the unique values or count the number of combinations of things. And so count is just another one that you might often find yourself reaching for in there as well. So you want like the mean and the standard deviation and the sample size, for example. Count is a very handy one to have. So if you just want to count the number of entries for each sex in our data set, you could do something like this. So here's my data set, take it and just count the number of entries for each sex in there. So group it by sex and just give me the number of entries in there. And it's quite a lot. So there's a lot of males and females, and then a bunch of NAs as well. And that's all our count is doing, and we can combine that. Okay, so there's also a sorting option in there as well. So you can arrange it by the output by increasing or decreasing number there, if you so desire. I don't actually use that terribly often. I use count, but I can't say I sort it too often. And in the same way, if you want multiple pairwise combinations, you can just feed that right into count. So I want every combination of sex and genus, just count how many entries are in my data set. So what's the sample size essentially for every sex genus combination? What's the N? What's the sample size there? And it tells you for every single one. There's a whole bunch because there's a whole bunch more rows down here. So we've got 31 females of this genus. We've got 1,200 females of this genus, and so on and so on. Only one of this. So for every pairwise combination, because we've fed in both of those variables, and we get all those counts back to us. And okay, all this is just suggesting that we can also arrange things as well. That's just a bit of a convoluted, I don't often find myself doing this kind of thing in practice, but you can of course string these together into chains. So if you wanted to, for example, get an alphabetical order of the levels of each of our genera, so we could sort genera in alphabetical order and in descending order of the count, just to flex our sorting muscles here, really, for nothing much else. You can also just chain these things together is the basic point being made here. But that's arguably a bit overkill. All right, so I think we're on our last batch, which is cool. There's like a last set of little exercises here. And some of them do get kind of complex. Let me have a quick look as they're going up. So they do, again, they build. So they may make use of all of our things, our verbs thus far. So filter and select, mutate, and now we're summarizing and grouping our summaries as well. And I will go back. I can show you just to show you the syntax of what summarize and group by. I might just leave it on that screen a little bit as well, because it can be a bit unintuitive at first glance. So we might have a crack at some of those. And they're actually the outputs of each of those are the numerical answers. So like if you think you have an answer, maybe just like chuck it in the chat, just the answer rather than the actual code to get there, and I can help you along the way and see how close we're each getting. Oops, sorry, get rid of that. I think that's more or less the bulk of it. I can show the very last thing is just how to write CSVs once we've gotten there, but this is kind of the last of it. So anything at all that comes up or you might be stuck on, I'm happy to chat through a bit. So where are we? Yeah, good stuff. All right. They also get pretty complex, so we may not make it through all of them, but by all means we can have a crack next week, or I can share things with you. It's no problem there. Drink back in a second. Somebody. All right. Anyone got a guess for the first one? Let's just see things. So what is it? How many animals were categorized at each level of danger? So that's our count, I reckon, would probably get us there for each level of danger. So let me have a look. That sleep. So there's my sleep data. Nice one. That looks pretty sensible to me coming in. So in terms of the actual value there. So what this is saying is take my data set, that sleep, and I just want you to count up every the sample size for every unique level of danger there. So danger level 1, 2, 3, 4, and 5, we have this number of entries for each level. So for every level of danger, what's the count? How many rows are in there? 19, 14, 10. That looks about right to me. Let's work. All right, now things are building up a little bit. What is the average body and brain weight for every level of predation threat? Cool. All right, so that sounds like it's going to call on our summarize and our grouping because we need some summary data. We need means, and we need means by a group, by some grouping structure there. So for every level of predation, what's the average body and brain weight? That looks like a fair way to do it there in the chat, but I'll work it through myself as well. So take my sleep data set with the average body and brain weights for each level of predation. So my grouping here for each level of predation, so I need to group by my levels of predation, which makes a lot of sense. And then I want summary information. I want you to summarize this data set for me. You could call it whatever you like. So call it body mean. So I want the average body and brain weights. Okay, so mean. And I've already forgotten. So it's called body weight. I want the average of that for every level of predation. BODI-WT. There's one thing I want. Let me just see if that even works. That does run, and that looks, roughly sensible. So I've got this new variable called body mean for each of 5 levels of predation. Okay, that makes some sense. But it wasn't just that I wanted, was it? It was brain mean, brain weight. So I want to create a new variable called brain mean, and that's the mean of all my brain weights. If I run that, seems to have achieved that all right as well. You may want to throw out NAs. I don't know. Let me just see if that makes a difference. Yeah, it does. So we want to, because I think otherwise it averages over our NAs. So there's a couple of ways you could do it. There was one in the chat there. You could individually say, for each of these, you could say, throw out my NAs, or I could actually filter the data set at the beginning to throw out NAs as well. Although, actually, maybe this is the better way to do it. Actually, that's probably the way to do it. I think it's doing that anyway. which might have just been a relic on my part then. It's good to be explicit nonetheless. So take my data set, and for every level of predation, I want 2 new variables, body and brain mean, and to fill those in, take the mean of body weight and brain weight in my original data set. Nice work. I'll chuck that in the chat. Other people have already beaten me to it. Yeah, okay, so now things start getting increasingly complex. Looks like I need to do some mutating for this third one. Start thinking it through. Okay, good sleep. What is the mean, minimum, maximum proportion of time spent in dreaming sleep? So there's dreaming, non-dreaming, and total sleep. So there is no proportion here, so I need to, oh, cool. You beat me to it. That's looking pretty suave in the chat. But yeah, so I mean, proportion of time, there's no proportions in my data set, so that means I've got to create something new. So I reckon I need to mutate my data set a little bit because I need to create this new variable so that I can then summarize it. And so my proportion might be something like, yeah, or dream prop sounds good. So here in my data set, I can see there's dreaming, non-dreaming, and total. So I just want a proportion, which that should give me. So the proportion of dreaming is a function of the total. Yep, proportion of time spent in dreaming sleep. That makes sense. And I'll just, again, building this up as we go, I'll run that. So there's dream prop. Okay, that exists, that's good. Let me crack on building up our little chain here. And then now that I've got the proportion, sorry, I want to summarize it. And there's no grouping that's specified. I just want the mean, minimum, and maximum of each. So I could do summarize. Mean, oh, let's call it dream mean. So I want the mean proportion. I want the minimum. I want the maximum. And I want you to save them in each of these 3 new variables for me. Mean, min, max, mean, min, max. And that is based on that variable that I just created here, dream prop. Chain that, take that, take that, take that. So what I'm expecting when I run this is a new data frame with 3 variables in it and just 3 values for those. No, of course not, because it's freaked out because I've got NAs. Need to be explicit and tell it to forget blank values. There we go. So the average proportion of time spent in dreaming sleep is about 0.18. The minimum is 0, and the maximum is 0.46 proportion of time. About half of dreaming sleep. Half of total sleep is spent in dreaming sleep. 1, 2. Great work, even though I was beaten to it. Yeah, very nice. Okay. Let's crack it. We'll get D, and then I'm just conscious of everyone's time. So let's have a look at what is the animal with the largest brain weight for every level of danger? Okay. And arrange the output by descended. Okay. Some complexity just for the sake of it then. Data set's always the first one. Largest brain weight. So brain weight for every level of danger. So it sounds like we want to group by danger level. And I want to know the largest brain weight at each danger level to the maximum brain weight at each danger level. And then I can sort the outputs. There's 3 things I need to do there. By the looks of it. So it's saying for every level of danger, largest brain weight at each level of danger. So my group is danger. I want, so it's just asking me what, okay, which is the animal? So it's just actually a filter. There's no summarizing that needs to be done per se. So I just want to filter out, or again, I think there's probably a few, okay, yeah, you could summarize as well, max frame loop. Yep, that'll probably do it just fine as well. So there's actually a couple of ways you could do this. This is just the one that occurred to me, but I think that one in the chat would, let's compare them shortly. Let me copy and paste that. I'll save that one. You're probably right by the looks of it. Oh, no, wait. I'll do this the way that initially occurred to me, but there could be a better way to do it. Brain weight. Yeah, because that would just equals, that is indeed what I meant. So here I'm just saying, well, just give me those rows where brain weights, I just want the maximum. So for every level of danger, filter out my data set just to leave me only with the maximum values of brain weight. Another way to do it would be to create a whole new data set whereby, yeah, you take the maximum of brain weight as a brand new variable. That should work just fine. So you can either create a whole new data set there by doing it, or you can just filter the current data set. I reckon they're probably going to be equivalent, I think. And then we just arrange. So you can use desc, which is a good one, or we can just use our cheeky little minus sign as well to flip the order in which these things are arranged. So it's by default low to high, I think is right. And so to go from high to low, you can either, you're exactly right, you can use descending, or you can just put the minus signs. Let me see what this looks like. And let me see what this looks like out of interest. Yeah, it's a slightly more elegant way to do it, isn't it? Although it's asking me what the animal is, I guess, with the largest brain weight at each level. So you'd need to then do a touch more work, because here it's actually giving me the specific animal as well, with the largest brain weight. But 640 at each level of danger. Now, hold on a sec. So how are these different? Which is the animal with the largest brain weight at each level of danger? Man, that's slightly dated. Yeah, so this is my little data set, which makes a lot of sense. So danger of 5, 4, 3, 2, 1. Those with the highest brain weights are horse, elephant, man. How does that compare to the output of this? yeah, so I just need the brain max brain rate. So those aren't the same, and it'll take me a minute to think about exactly why. So I'm filtering, I'm just retaining the brain weights that are equal to the maximum brain weight for every level of danger. Just summarizing. Who's the same? No, not at all. That's a good question. I just leave it with me. I think slowly when hit with these things. I'm going to stick them both in there. I will have to, I'll get back to you next week on exactly why it's different, because it's not immediately, I'm sure it's very simple, but not. What if I drop NAs from, oops. Actually. Ah, that was the only difference. Okay, I just threw out all the NA values as well. So they are exactly the same. A and B, A and B, yeah. So whether the results are totally equivalent, I was throwing out NA values beforehand and you weren't, that was all. But now that we both throw out, oh, neither of us do, you can see that our brain weights are exactly matching. Mine has the species still listed in it, which is handy if that's what you're after, but our actual brain weight values are exactly the same. And you could just tack on, you could add a little something in your summarize whereby there would be a way to just tack in the species names again, but two different ways of doing the same thing. Nice work. So those are equivalent. I'll leave F because that's a long one, but E is at least a relatively short statement. Did anyone have a pun to, can you keep other columns after using summaries? No, because it's a completely new data set. So it wouldn't make sense, if that makes sense, because when you're summarizing, it's crunching down a lot of data into a little bit of data. So it's like taking a whole column and taking a mean, for example. So it wouldn't make sense to keep the raw data because they're completely different shapes and sizes, if that makes sense. So if you, like here, if we're taking just the maximum, or like here we're taking the mean of dream prop. So that's taking, those 50 values and calculating a mean. So the resulting data set is just one row by one column. You wouldn't be able to keep the raw data as well because they're completely different shapes. So they're completely new data sets. Whenever you're using summarize, it's a whole new data set. So no, it'll only retain those things. It'll only create those brand new columns that you tell it to, because by necessity, it's a summary of a much bigger data set. If that makes some sense. So in that way, it's creating a whole new data set, smaller one. So no, we couldn't keep the raw stuff. Good question. All right, we'll do one last quick one, that sleep. So this is something, what have we got here? What do I want to know? yeah, as always, there's a bunch of ways to actually do this. I just want to know how many rows have missing data in them. These are getting tricky now. So it's introducing concepts on the fly. So it's totally cool if these are not immediately obvious. But here I just want to, so how many entries? So ultimately I want a single number in the end. And I want to find how many rows contain NAs. So there's this function called complete cases that we can use. Quick look at the help file. Function. There we go. So you can feed in like a data frame to complete cases here, and it'll tell you, it'll say true, false, false, true, false, false, true, false. For every single row, it'll tell you, well, whether or not that row contains missing values, true or false. So we could make some use of that by filtering based on whether or not our rows contain complete cases or not. So by whether or not complete cases returns true, as in they are complete, or false, and they're not complete. So we could filter our data just to return those rows which do not contain complete data, complete cases. So there is an NA in there. To do that, I'll show you, we'll start by doing the reverse. So we could do complete cases. Let's have a look at what that looks like. That sleep filter. So what this has given me is every single row in my data set, that sleep, it's filtered out just those rows that have complete data in them. So there are no NAs anywhere in this data set. Cool. So these, it's filtered based on whether or not the rows are complete. And it's just giving me the ones that are complete. And if I wanted to count those up, I could do, well, how many rows are there? N row, give me the number of rows. And there are 42 of those. But it does technically ask for how many rows contain, so how many rows are incomplete? So what's kind of the opposite of this? I guess you could, again, there are a few ways to do it. You could probably subtract that number from the original size of the original data set if you want, or we could just use this exclamation point to flip, to invert the meaning of our function, which applies to a lot of different functions. You can, because thinking back to our relational operators, the exclamation point means not, just as that is equals, that is not equals, that is less than or equal to. So this exclamation point always means not. So if I just chuck that in there and say, take my data set, that sleep, filter it based on how many of these rows do not contain complete cases, and spit out the final value for me. So there's 20 rows in there which contain some NAs. Complete cases summary, yeah, that looks interesting. And complete cases. Oops. Actually, no, I think that might have been, that's a good question. Let me double check what I was doing that for. Yes, that's, yeah, you're exactly right about the dot, because it expects the data. It's not actually a part of the tidyverse, this one. It is a base function, so I did indeed need to use my little placeholder here. So that's what that's doing. But there was a clever, oops, that's the complete cases. Is that right? That's the complete cases summary. I'm not sure that's quite getting me there. Whoops. Then I might be misunderstanding.
I didn't use the filter.
Oh, sorry. Yeah, geez, that's exactly, yeah. Okay, good stuff. Oh, brilliant. Wow, that's pretty nice as well. Yeah, that makes total sense. Yeah, so you're right about filter. I did use the dot, but that's a lovely way of doing it. And that tells you both. Yeah, cool. That makes a lot of sense. It's just an interesting bit of summary data you're after. So it's saying there are 42 complete cases and 20 incomplete cases. Yeah, actually, that's a nice way of doing it. Cool. For sure, I'll paste both of those in there. My way is way more convoluted, so I like the second one. For sure. Yeah, very nice. I might leave, we'll leave F, we can come back. That can be our homework challenge for next week if we so inclined. I think there's only a couple of things left anyway. It's really just last couple of points are the complement to reading our CSVs. We can also write them, of course. As a little example of how sort of a workflow might go using some of our clever little new functions that we've learned along the way. So we could do something like create this new, take our data set, let's throw away any rows that contain missing data. And let's save it in this new object here called .ecoclean. This is our clean data. And again, this is nice and reproducible and transparent here. So I'm creating a whole new data set based on this existing data set in which I'm just throwing out all those incomplete cases and I'm saving that. Here's what it kind of looks like. And I've just also plunked this here in case you want to come back through and compare your output to mine and actually do it manually. But yep, those look like complete cases to me. And then we can write that, we can output that, we can save that to our computer, we can share that with our friends. But now we've got a whole complete, transparent, reproducible little workflow for how we've taken something in, summarized it, created new information, manipulated it, changed its form, shape, all sorts of things. But the raw data are completely untouched. We have a nice little reproducible, rebuildable document that tells us exactly what we've done to our thing. And then we've put the output for further use into the future by ourselves, by others, what have you. That's very similar as well. There is a write.csv, and just as the question was brought up in the beginning, this is the tidyverse version. There's also a base version. They're very, very similar. So if you accidentally use one or the other, it's not a big deal. They just do things. There's some subtle differences as to how they save it, but nothing you need to worry about too much. So that was a lot. I know that was a lot. I know that's a lot on a Monday morning. I'm really grateful for you sticking with me. But by all means, if you've got any questions or anything as we go through and keep cracking on, just, we can come back and revisit things if you're back again next week. Just like email me, chat. Always happy to chat about stuff. But hopefully at least it gives you a bit of a running start, an introduction. It's a very different way of thinking about things, I know. So you've all done tremendously well, especially if this is like the first time you've heard about, pipes and wrangling in this sort of a form. But hopefully you at least get a sense of the potential of these things for sticking with our reproducible workflows and creating something that is ultimately human friendly, even if right now it's a little bit perhaps on the tricky side. But yeah, by all means, get in touch with any questions or anything, and I may or may not see you next week. Next week's fun. I love plotting and data visualization. So if you're interested in that, it'd be cool to see you. But otherwise, thank you for your time and for coming along. It's just wonderful. Lovely to see you all, and have a great afternoon.